When the rapid growing eucalyptus tree pushes out its leaves, it discloses one of the secrets of its ancestry. Some of the leaves, like those at the top of the branch pictured above, are narrow and long. Others, lower down, are much broader. On a single tree, it is common to find 5 or 6 different kinds of leaves, seeming, when laid side by side, as though they must have come from separate plants. The history of the eucalyptus, as disclosed by its leaves, its quick growth, and other characteristics, is that one time it was an herb, perhaps an annual. To fit themselves to some new environment, its ancestors succeeded in establishing themselves as perennials. But this change was so recent that the evidences of the transition are still to be found in the leaves of all young eucalyptus trees today. Right here on this experiment farm, spoke up Mr. Burbank, you might find hundreds of evidences of heredity, more striking than that. More striking because they are the evidences of heredity in plant life instead of in animal life. Right here, said he, you will find plants which show tendencies unquestionably inherited from a line of ancestry going back perhaps 10,000 years or more. Tendencies, some of them, which now seem strangely out of place because the conditions which gave rise to them in their ancestors no longer exist. Tendencies like those of the cactus and the blackberry to protect themselves from wild beasts, when wild beasts are no longer enemies. Tendencies to deck themselves in colors designed to attract the insects of a forgotten age. Insects which perhaps no man has ever seen. Where some incredulity might be expressed as to whether the bear had not actually been taught to fish for salmon or seen another bear perform the act, there can be no such question in the case of heredity in plants. Here, said he, as a bed of sweet peas was approached, is a plant which has inherited the climbing, twining tendency. That is an evidence that, at some time back in its history, this plant has probably been crowded for room. Plants which grow high do so usually because at some stage in their existence they have had to grow high to get the sun and the air which they need. Low-lying plants like the pumpkin, for example, give evidence that they have always enjoyed plenty of space in which to spread out. The bear of your story may have slipped away, unknown to its keepers, and seen another bear fish for salmon. But if these tendencies and traits, and if the ability to perform the feats necessary for existence are not passed down from mother to son, if they do not come down through the line of ancestry, if all of the old environments of the plant have not accumulated into transmissible heredity, what enables that sweet pea to twine around the stake? A closer observation of the sweet pea will show us that its tendrils are really modified leaves, produced like the spines of the cactus by ages of environment which, added up, combine to make heredity, and that their actual sensitiveness to touch is so highly developed that they almost instantly encircle and hold fast to any suitable support within their reach. It would be interesting to take a motion picture of a sweet pea as it grows, as similar motion pictures have been taken, making our separate snapshots one every 3 minutes instead of 15 or 16 to the second, so that the reel would cover a period of 15 days. Then, with a 15-day history recorded on our film, to run it through the projecting lantern at the rate of 15 or 16 pictures to the second, thus showing in 7 or 8 minutes the motions of growth which actually took 15 days to accomplish. On the screen before us, with quick darting motions, we should see the sweet pea wriggle and writhe and squirm. We should see it wave its tendrils around in the air, feeling out every inch within its reach for possible supports on which to twine. We should see, by condensing half a month of its life into an 8-minute reel, that this sweet pea has inherited an actual intelligence, slow in its operation, but positive, certain, and inherited intelligence which would be surprising even in an animal. The two dahlias shown in this direct color photograph print illustrate the freaks which heredity sometimes plays. Sometimes when two widely separated strains of heredity are brought together in a single plant or animal, the result is a blend. But in these dahlias, as will be seen, some of the petals take back to one line of ancestry while others take back equally distinctly to another. No man can predict the outcome when two separate strains of heredity are mixed. All through plant life we find these undeniable evidences of heredity. I have here, for example, two tiny seedlings which look almost alike. They are distantly related. One is the acacia and the other the sensitive plant. The tiny seedlings shown here are the sensitive plant and its unsensitive The tiny seedlings shown here are the sensitive plant and its unsensitive cousin, the acacia tree. Although these plants are clearly related and resemble each other as seedlings, one has a sensitive, shrinking tendency while the other, though through its lack of it, testifies to an entirely different heredity. In this print, it is seen that the sensitive plant at the left folds its leaves into the smallest possible compass, making itself as inconspicuous as possible to an approaching enemy. The actual photograph was snapped less than 2 seconds after the plant had been touched, but in that brief time, as is shown, the transformation was complete. The acacia with its different heredity shows no tendency to fold up, even when crumpled in the hand. Much as these plants look alike, they bear witness to the fact that they have within them two entirely different strains of heredity. The acacia will permit us to touch it and handle it without showing signs of disturbance, but its cousin in the same soil and of the same size immediately folds up its leaves in self-protection at the slightest touch. From this we read the fact that one branch of this family has found it necessary to perfect a form of self-defense, while the other has had no such experience in its life history. I have been much interested lately in an experiment with common clover in producing clover leaves with wonderful markings. The only way in which I can account for the markings with which some clover leaves will bedeck themselves is that, in the heredity of the plant, there was a time when, not being poisonous itself, it tried to simulate the appearance of some poisonous plant to protect itself from insects. At first thought, it might require a stretch of the imagination to understand how this could be, yet a closer inquiry shows that the process was as gradual and as surely progressive as the transformation of the cactus. The clover leaves shown above reveal a strange inherited tendency. It is Mr. Burbank's belief that the white markings and the black splotches, which can be readily distinguished, represent an attempt on the part of the plant to simulate a poisonous look as a means of self-protection. Although the tendency to protect themselves with these warning streaks and blotches of color is very strong, yet in all of his experiments Mr. Burbank has not found a single clover plant which was actually poisonous. In clover, as in other plants, there has always been variation. Some few individual clover plants have always had the white and black markings. At some time in the history of the plant, those without the markings have been destroyed, and so, responding to this new environment, the markings became more and more pronounced until now we have not only white triangular markings, but ugly black splotches going clear through the leaf. From these markings we can read the history of the clover, most of the family having plain leaves inherited from an ancestry which found no need to protect itself from an enemy, with an occasional outcropping of poisonous-looking color splotches, the inheritance of scattering environments in which self-protection was necessary. Or we might consider the ice plant, so-called, which protects itself from the heat of the sun by surrounding itself with tiny water drops which have the appearance and serve the same purpose as icicles, or the wild lettuce, known sometimes as the compass plant, which turns its leaves north and south so that only their edges are reached by the sun, or any of a number of other strange protective measures which plants have perfected, all manifestations which would be impossible if heredity were not an ever-present controlling influence. In this direct color photograph print, it will be seen that the stems and leaves are covered with formations which appear to be tiny icicles. The plant is known as the ice plant, and the icicles in fact are stored up moisture which it saves up against the heat of the sun. The need for this extra moisture is not apparent where this plant now grows, and it is reasoned therefore that the plant has been stranded at some time or another in its history in some unusually hot, dry climate. We have, too, in many parts of the country, plants which have learned to snare and trap insects and even animals, and to digest them and to live on them. Among these carnivorous plants are the common pitcher plants and the Venus flytrap. The pitcher plants, instead of belonging only to one family, are to be found in a number of different families, thus showing that environment has produced a similar strain of heredity in separate kinds of plants, which are not kin to each other. One of the pitcher plants, which grows abundantly in the moist places of the Sierras and in northern California, even catches frogs, small animals, and birds. The plant seems especially devised to lure the animals into its pitcher. Above the pitcher is a little lattice and an opening, like a window, through which the light can shine. The insects and the animals see a haven from the sun and rain, and as they go in, there are little fingers on the plant which push them along and keep them from coming back. Once securely in the trap, the plant secretes a digestive juice, like our own gastric juice, and absorbs the animal life as food. The pitcher plant shown here, which grows in the high mountains of California, has perfected an ingenious contrivance. An ingenious contrivance for catching and digesting insects. At the top of the pitcher, so-called, seen above, there is an opaque lattice work in the interstices of which is a translucent mica-like substance. The insect, entering from beneath in search of shelter, finds itself in a cozy chamber, well lined and weather-proof. Once inside the chamber, however, it discovers that it is being swallowed irresistibly, and the plant finally deposits it in the stomach below, where it digests it with a secretion akin to hydrochloric acid. There are several other known carnivorous plants, showing that at some time in their ancestry the soil has not given them sufficient nutriment for their needs. In these traps, it is common to find all kinds of insects, including the undigested wings and legs of beetles and grasshoppers and the bones of toads and frogs. Is this not a more wonderful manifestation of old environment recorded within a plant in the form of heredity than even that of a bear which seemed to have inherited the intelligence and skill to fish? To my mind, said one of the scientists, the byproduct of your work is fully as interesting as the work itself. The viewpoint which you get on the forces which control life is of even greater attraction to me than the wonderful productions which you have coaxed from the soil. A byproduct? No, said Mr. Burbank. These things are a vital part of the day's work. Heredity is more a factor in plant improvement than hoes or rakes. A knowledge of the battle of the tendencies within a plant is the very basis of all plant improvement. It is not, as you seem to think, that the work of plant improvement brings with it, incidentally, a knowledge of those forces. It is the knowledge of those forces, rather, which makes plant improvement possible. There are really, after all, only two main influences which enter into the makeup of life, only two influences which we need to direct in order to change and control the characteristics of any individual growing thing. The first of these is environment. The rains, the snows, the fogs, the droughts, the heat, the cold, the winds, the change in temperature between night and day, the soil, the location and shade or sun, competition for food, light, air, the neighbors, whether they be plant neighbors or animal neighbors or human neighbors, all these and 1,000 other factors which could be thought of are the elements of environment, some pulling the plant one way and some another, but each with its definite, though sometimes hardly noticeable, influence on the individual plant. And the second is heredity, which is the sum of all the environments of a complex ancestry back to the beginning. Just as with the bear, if the story be true, so in plant life, in every seed that is produced, there are stored away the tendencies of centuries and centuries of ancestry. The seed is but a bundle of tendencies. When these tendencies have been nicely balanced by a long continuation of unchanging environment, the offspring is likely to resemble the parent. But when, through a change of environment, that balance is disturbed, no man can predict the outcome. So when a seed is planted, no man can be sure whether the 20th century tendencies will predominate or whether long-forgotten tendencies may suddenly spring up into prominence. So when a seed is planted, no man can be sure whether the 20th century tendencies will predominate or whether long-forgotten tendencies may suddenly spring into prominence and carry the plant back to a bygone age. How can seeds store up the tendencies of their ancestry? Someone asked Mr. Burbank. How can your mind store up the impressions which it receives? He asked in reply.